This is week 11, and today we shall be just focusing on two things. One is we just started learning about convolutional neural networks, and then AI policy of Japan, that how Japan AI policy differs from the others and where Japan stands today in AI. So perhaps Japan is a country that they are more prone to living with humanoid robots, and it seems like soon they will be part of their family. As it says, more than any other nation, Japan tends to feel comfortable with the idea of humanoid robots entering the homes. And also to increase attendance in the school, now they're just making a robot to attend classes, and the students feel more comfortable and more enthusiastic to come to school because there is a robot sitting with them. So we will going to spend more time on this. Last time I want to review this today as well. The classical traditional machine learning, how then it is different from the deep learning. So we just started learning about the linear classifiers and how to deal with uncertainty, and this shall lead us to transformers and then large language models. So this is what I intend to quickly review what we did earlier. Classifiers, traditional machine learning, linear classifiers, dealing with uncertainty, neural networks, and then I'll spend more time with convolutional neural networks and see that how we can generate code, especially from ChatGPT, to implement convolutional neural networks. And then I'll spend time learning about Japan AI policy and its strategy. So as I the other day, let's quickly just go over the content. This is the PhD work of Dr. Usman Akram, who had hundreds of publications almost in this area. And this is what he started in his PhD, taking a fundus image and then extracting features. And only an experienced person, a person with domain knowledge, would tell that what type of features you require. So first thing is, usually if you are really handling a sophisticated problem, you got to have somebody who is domain expert. You have to sit with him and he'll explain, and then you got to know a lot of signal processing and image processing to extract those features. So that usually requires very complex mathematical operations to perform. Like in this case, we wanted to, because they look at these liens, and we wanted to extract the liens and the disk, the optic disk where got to identify this. And then for that we had to first do the blood vessels segmentation, and then taking out the blood vessels. And once we took out the blood vessels, we were left with liens with a mark where the focal, the disk, optical disk is. And with respect to this, then we had to extract many features, like tens of features that you extract. And then you got to learn about what features are actually helping you to do the classification. And so the feature selection, and then once you have feature selection, only then you can have a classifier to classify into 1, 2, 3, 4 or multiple classes. So, so this is the challenges, and so not everybody can just work in any area. So you got to be good in signal processing, image processing, and only then you can be machine learning. So example is just added this. Let's say you are asked to classify these two. Perhaps you say color is good enough. So if you know the color of the image, like you take color from 3, 4 different locations, and then you do the classification. But then you may find that some of the cucumbers have color like potatoes, so you got to add another feature. Let's say you add the aspect ratio. So with these two features, you do the classification, aspect ratio and color, where here you are yellowish color or green color, and aspect ratio of cucumber and the color is green. So most of them will fall here. So you do the classification. But what if you have more colors to classify. So it becomes then a challenging problem. You have to think about it, that what type of features you are going to extract in an image so that you can just do the correct classification. So 2 features will not be enough. So the problem start becoming more and more and more and more complex once you add more objects in the class. Just imagine this ImageNet challenge, which had about 14 million images and 21,000 different classes. And they challenge everybody to design a classifier. And this is pre-neural networks, kind of pre-convolutional neural networks. So people would still try to kind of extract features, do something to do the classification. So it was the winner in 2010. So this was the team, and then there were the 5 winners. And everybody was using something which is if I saw this paper, very challenging to even understand what they're talking about. The descriptor coding plus SVM, and then Fisher kernel plus SVM, and we know KNN, and so everybody was using a different type of algorithms, and still they were not very accurate. Like the accuracy was 0.28, 0.34, 0.58, and even 0.79 in top 5. So you can just say 80% of the time they were wrong, but still they were in top 5. So classification was a challenging problem for people, and especially if you have multiple classes. So this is the paper where the people from NEC, University of Illinois, Urbana-Champaign, Rutgers, who won the challenge in 2010. And then every year there were submissions, and they were improving, from 28.2 to they were going down, down, down. And as I mentioned the other day, this was very significant improvement. Usually you don't see this type of improvement, that you improve this much, and you were way ahead of the second rank in the competition. And this is where he used the convolutional neural network. And because of that, in subsequent competition, everybody just started using convolutional neural network as if it becomes the standard, that you got to just experiment with the convolutional neural network. Let's not even worry about other classifiers, especially a challenging problem. It's not that every problem you start solving with convolutional neural network because you need a humongous amount of data, but a challenging problem must be solved. And it was Google and then the Microsoft 2015. They have taken over human as well. So this ResNet has taken over humans, and then they are continuously improving, and have gone to accuracy of 0.023. Just look at this, that how much they are accurate now, starting from 0.28 to now 0.0 something. So they are just, and then a big transition where they just started focusing on convolutional neural networks. This is the ResNet. We'll maybe cover this, but these are the different networks. And the good thing about them is you don't need to worry about extracting feature, doing all the math, complex math, and you just are trusting the humongous amount of data and humongous amount of computational resources you have at your disposal, and just a network which you believe resembles a brain, or just something which can learn by itself. And you just keep passing data, sometimes for days, and keep making this network learn. And learning means just the weights, that they got to learn the weights. And end of the day, there are 1,000 classes, and it'll show the distribution, probability distribution of the class, and the one which has the maximum value is the one which your network is basically classifying that it should be this. So every neural network, no matter what it is, would have something like this. So that's why it is called deep neural network. It's going deep into from input to output. It goes through so many steps and so many weights that are adjusted so that it self-learn to extract features. The good thing about these is that once you are in the last layer, which is usually called the fully connected layer, so that layer is only that it has by itself learned the feature instead of you asking an expert. So now means once you have the features, then you can apply any machine learning technique. May it not be neural networks, may it be SVM, may it be anything. And once you have the feature, it is not specific to even classification. You can do a lot more than just the classification, because the only thing DeepNet is doing that it is extracting features from the data that you will feed in, and the features can be used for classification, for segmentation, for other object detection, for so there's so many things that you can do once you have the features detected without having a smart guy who is sitting with you and telling you that this should be a feature, this should be a feature. So this is, again, we covered in the last lecture, but because I would still, if there is any question, please do ask. Neural networks basically also handles nonlinearity. Okay, if your data somehow, your features are such that they can so beautifully separate every class, then you are done. Okay, features are such. So feature engineering becomes very important sometimes. So the features are such that they can just give you very clean. Yes.
सर मैंने एक क्वेश्चन ये पूछना था कि क्या आप एक इमेज को लेके मैन्युअली ये बता सकते हैं कि रेजनेट किस तरह उसकी फीचर एक्सट्रैक्ट करता है और सीएनएन और रेजनेट में फीचर एक्सट्रैक्शन में क्या मेजर डिफरेंस है?
Apparently, you can tell about the structure, but you cannot tell that how it is actually extracting the features. तो वो जो explainable AI वाली चीज़ है ना, like people are now just trying to know that how it has actually extracted the features. लेकिन अभी हम सीखेंगे कि कुछ हमें पता होता है, like because हम इसमें convolutions कर रहे हैं बहुत सारे, and once you are doing convolutions, so at a broader level you understand. ठीक है कि अच्छा हाँ ये हो रहा है, which makes sense kind of, कि हाँ ये समझ आती है बात कि this is the fine features, and then the medium features, and then this is the high level features. So things start making sense. But कि क्या there is exact कोई mathematical formula है या explanation है, उस तरह से नहीं है. And then why one architecture over the other? Yes, आप थोड़ा सा उसके बारे में कह सकते हैं कि इसने इस चीज़ को इस्तेमाल किया है because to help him achieving this, कि ये उसमें shortcoming थी, उसने इससे इसको पूरा किया. And there are so many different architectures of deep neural networks, and they are getting even complex. So I'll show you some of those architectures. And the rationale may be behind one over the other. Okay? So really the whole reason of going through deep neural networks is you don't want to worry yourself that how features are being extracted. Okay? That's the main reason. कि आप कह रहे हैं मुझे सवाल पता है, उसका जवाब पता है, and I know millions of these questions and millions of the answers, and I somehow want this black box to train itself, spending as much time as it wants and having a lot of non-linearity added into the architecture, that whatever the decision space is, it should just create that decision space. And we will understand कि decision space है क्यों, किस तरह से non-linear है, किस तरह से ये neural networks उस non-linear decision space को mathematically बना लेते हैं. Okay, so that's as a matter of fact, it's a challenge. Here you can use the math. So you can see this and you say, oh, there I can just fit a straight line. If I fit a straight line, then I have this classifier. और so linear classifier की problem आसान है, और उसमें मसलन ये हम we are going to spend more time learning about the SVM. This is one of our technique to do linear classification, and it fits in sport vectors and tries to find out the widest margin between the two classes. Okay? So this is a technique, but it's a technique, people have mastered this technique, and as you saw the competition 2010, most of the people were using the SVM to do the classification. So in 2010, the winner was using SVM. So means that he could able to extract features which had separated those classes, and still he showed very interesting images where he failed because the features were kind of looking same. So this is one of the techniques, and we are going to spend time where we will see that how these sport vectors are actually calculated, and how there is this line which do the bifurcation. And then, because in the training data, why you want the widest gap? Because once you are actually doing the testing, there may be some of these who would fall here and some of these who would fall here, but you have really separated them so that once you actually test it, you still have margins that where there may be other test samples. They may be on just one side or the other side. So you try to make sure that this line is in the middle of the widest gap you find in the data. And the features are such that you could actually separate. And even SVM, like we saw a kernel, Fisher kernel based SVM, they could actually handle nonlinearity, some nonlinearity, and we will see that how they do.
What about overlapping?
Yeah, then those will be errors. If there is an overlap, for example, there will always be some errors then. Okay, so in this, so you say, so there are two aspects. One is there is overlapping, means that your features are not good enough to actually make them just part of one group, so they get into the other group as well. So you may have to add another feature. As I was showing you the cucumber that colors like a potato, and you say, oh, this is my error. So you find out all the errors, and then you start thinking that I need to add more features because still I'm getting errors. So you add more features, And the other technique is you perceive all the possible features and just throw them and then start taking features out. And this may be just exhaustive. Okay, one feature each, then two of each, then three of each. Then there are algorithms, like one we studied was PCA, Principal Component Analysis, which could just have 3 components, 4 components, and where those are not features, those are linear combination of features. You say, I'm still okay. So the one which is not participating will be multiplied with almost a 0. So its contribution will be out of your algorithm. Okay, or other is, no, you actually go and find out the features which are not really helping you out. So this is where you have, a plane and hyperplane. If you have 3-dimensional feature, if you have 4, that's why it is called hyperplane. Only till 3 dimension you can visualize. After that you cannot visualize. So it becomes a hyperplane, okay, which has 1 dimension less than the dimensionality of the data. Okay? If it's a 2-dimensional, so your separator is a line. If it is 3-dimensional, your separator is a plane. If it is 4-dimension, your separator is something solid which is in 3 dimension. If it is 5th dimension, then you have a separator which is 4th, which is 4 dimension. So this is how basically kind of your algorithm is. That sometimes you add a bias, but it is like you can actually plot the linear classifier which you saw in terms of a perceptron as well. That you have a feature is to be multiplied with some weight, then you have another feature, it is multiplied with another weight, and then you have your last, let's say you have only 3 features or n features, it is multiplied with this. Okay, and sometimes this is just the bias that you are adding. So this is constant value, so there is no feature, you have 1. So this will become a B. So if it is 2-dimensional, so it will look like an equation of a line, which says W1 x1 plus W2 x2 plus b. And if you make it equal to 0, so on one side of the line you will have one class, and on the other side of the line you will have other class. Like if it is greater than 0, you have one class. If it is less than equal to 0, you have another class. So equation of a line, and if it is, once you put a point in this equation and you get a negative value, you say it is one class. If you get a positive value, you say it is another class. So it becomes a classifier, a linear classifier. Okay, it may be 2-dimensional, 3-dimensional, even it may be 1-dimensional, just something greater than equal to 0. There is just a constant. So, but the limitation here is that it is linear, and usually it converts, if it is by is only 2 classes, so it is either 0 or a 1, or -1 or a 1. So you have only 2 classes. And it only is, your data has to be linearly separable. If it is not, then this will not work. This will give you an error. If the input vectors are non-linear, it is not easy to classify them correctly. For example, if somehow data is like this, and you plot it and you see that there is no way you can classify this, using a linear classifier. If your features are like this, good. If your features are like this, it means that you got to do something about it. Okay, either you transform your feature, take it some transformation so that they basically change, or sometimes there are techniques where you increase the dimensionality of the data by taking a transformation, where again you are trying to fit a linear classifier, and that's the constraint. Constraint is still there. So you are going to transform this, and you assume that after transformation you will able to fit a line, okay, or you fit a plane so that you get it right. But
just to add one thing, in medical, because I did
yes, yes, yes.
that, they have very good terminology of a control group.
Yes, bilkul. Yes.
If the value is below the threshold, they take it as one singular value. You can keep it 1 or keep it 2, and
yes.
if it is the threshold, then it goes to the next class.
Yes.
So I find that as a very amazing.
Yeah, so you are saying if you are multiple classes. Yes.
Even if you point
yes.
to multiple classes, this is what they did.
Yes.
When I took their data out and I was asked them, what is the threshold? They said if the blood value in certain context is greater than 11,
yes.
then we take it as.
So you are saying it's a linear classifier and there are multiple lines, yes. And you say if it is greater than threshold, it is here. If it is this, it is here. If it is this, it is here.
They call it control.
Yes, yes, bilkul. So that's how you are basically, bilkul sahi hai. So, so if you have like such type of a decision space, okay, so it becomes very challenging. And this is where, no matter how big a mathematician you are, if I ask you to write a mathematical expression, to draw a line which look like this and look like, so this seems like it's a good, it has separated whatever features you have taken, so they are not mingled into each other. But writing this mathematical equation is almost impossible. Okay, you cannot just trust that any mathematician could actually come up with a mathematical expression which could draw these type of surfaces. So this is where neural networks, they come into play, that you don't need to worry about it. Let us put some nonlinearity and so many nonlinearities adding together, creating this surface and creating this equation, even in 2-dimensional, in 3-dimensional, in 4-dimensional. So that's what kind of neural network solves this by just generating that nonlinearity, because linear classifier is not going to work, or simple transformation may also not work. A simple transformation, like still you use SVM, but you uplift the data in another dimension and you put a linear classifier, this will not work. So you got to need a nonlinear classifier. It seems like you got to need a nonlinear classifier. Otherwise, you will only able to handle a subset of problems, or you got to get into very, very complex feature engineering, which is then is difficult. So here is the example which I showed you earlier, that like you want to classify these 3 penguin, and you have their flipper length and their body mass, and you find out this data, there's no way that you can classify it. Okay? So, and then we took this example as well. And this is another problem, which is the regression, that sometimes you don't want a class, you want a value, a probability value, that this is how much probable it is. Like sometimes you have a classification problem where you put a threshold. If it is greater than this, then it is in this class. It is less than it is in this class. But here you want a value, that what is the probability I'm going to put a jacket, knowing the temperature and the wind speed. Right? So you collect data, and you have you can just put a classifier anywhere. So anywhere, or if you are using SVM, you know the widest gap you have. So you put a classifier in between that. So you are collecting more data, and then you realize that many a times you yourself are not sure. Okay, so you want to capture that uncertainty in your decision, that whether you are going to put a jacket or not put a jacket, and you want this to be part of the model, because now you want a value, a probability, that this is how much probable it is that I'm going to put a jacket. So sometimes it is important, especially in once you are having social media advertising, you want to model that how many people are going to click on this if you have an ad, and you also want to see if somebody has clicked here, what is the probability that he'll click this as well. And so you want to model this, and the modeling this is, you say it is only 0.01 probable that this type of a person is going to click, or here it is 0.9%. So you push your ads accordingly. So you push your ads, you push your campaign accordingly. So this has many applications. So here is that we said it is the how to capture uncertainty, and this will lead us to neural networks capturing uncertainty. So capturing uncertainty is this is simple 1 and 0, but this is where you can capture uncertainty if somehow you can have a mathematical expression of something which look like this, where you say that here I am sure that I am going to put a jacket. Here I am sure I am not going to put a jacket. But here it depends. I may or may not. Okay. So you say because now there is uncertainty, I want to capture this uncertainty in a mathematical expression so that the value I get is I know the probability. So this is how you basically, because now there is some uncertainty in your decision. And you say, I want this to be mathematically written, okay? And this is what the neural network does also. Like it has, otherwise it is a linear classifier. It is weights multiplied by features. It's a linear relationship. It adds nonlinearity by whatever value you get. It basically passes it through a nonlinear function. So it becomes a nonlinear. And once you pass it through a nonlinear function, then you are plotting this. Once you have multiple values coming out of your your linear multiplication of weights with the features. So that's how you add. And people thought that exponential is good. Some thought tangent hyperbolic is good. Some thought just a max is good. So they said perhaps this is exponential is, as you know, exponential increase. So we know that exponential of 0 is 1, and then you have negative values, it is 0, and for positive value exponential goes to kind of infinity. So exponential is something which is a nonlinear function. Okay, they said yes, perhaps if I bring, so they are the mathematician, they could figure out that this is type of a curve they can plot, because you don't want this curve, you want this curve where it is going to 0 and it is. So they realize that they can, or this curve. So they realize by having this exponential in the denominator minus of the variable, they can plot this curve, and still it is passing through 0.5. You want to control its slope. So they add a weight which is to be trained. Okay. So they add a weight. This is the exponential. So in order to shape the curve like this, they add this theta. And this is what you got to train, that how much nonlinearity you want. So theta is something, z is your feature, and theta is a multiplier, a linear multiplier. It is, if there are two features, then two thetas. It is the same thing, w1 x1 plus w2 x2. It is same. Okay. So, and then you have to shift it, so you add a b. So precisely what we were doing before, and then passing it through a function which is a nonlinear function, which will take its minus exponential, add 1 and then put it in the denominator 1 plus this, it will create this curve. Wow, so you are done. Okay, so they said why not I have, so this is where you add theta to move this left and right, because we want to move it left and right as well. So this becomes the function, and this is precisely the same what we started with, and you put it through a nonlinearity which is sigmoidal, maybe different. So you can have this taken anywhere, okay, depending upon your data. It will learn from the data and it will move it to a temperature where you are uncertain. Okay, so and so it will, so this becomes our mathematical expression, which I was saying it is difficult. So up till now, mathematician can handle this. Mathematician can come up with this formula and we are fine. So I think it's not that complex. Coming up with this formula is not that complex. But here your theta, theta this vector and this, they are to be trained to primarily give you the best curve, which represents your data the best. If it goes into two-dimensional, so there are two features, so it becomes x1 theta 1 plus x2 theta 2 plus theta naught. So it becomes a linear expression. Okay. So this is what you have to learn. This is what you have to learn. X1 is your temperature. X2 is your wind velocity. Okay. So you put in all this data, and then you are training thetas to find out where you have minimum error. So all the points fit into the curve ideally, or if they are not fitting, they should be very, very close. So it's very simple. Like you have points like this. Okay. You know they are not in a straight line, but you can fit a line that basically best represent these points. So you try, and you may have a line which minimizes the error. What is the error? The distance of all these points to this line is the error. Seems like that. So you can fit in a line. But if it is not even representing a line and the data is like this, and you are trying to fit a line, what will happen? So your error will be a big number, and that will make you realize that you are trying to fit a line into something which is not really a line. So there you got to know that you have a lot of error. It means you need to change your classifier from linear to something else. Okay. So this is yes.
In this training data, it is possible that for the same values of x1, x2, we have different results, right? For example, you may prefer wearing a jacket.
Yeah, precisely. This is the challenge. One is your personal data. Okay, your personal data. You are collecting personal data, and you are saying, okay, this is my personal data. Here, I am not. So this is the temperature and wind velocity. You are saying, I'm going to put a jacket for sure. And here you are saying, I am not going to put a jacket, it is too hot. And here you are saying, I am confused. So you note your data. But now you are a departmental store and you want to find out that at what temperature and wind velocity people usually put on data. So now here, the data of many people. Okay, some people may want to put a jacket here, some here, and it is still going to try to fit in a curve to find out the best fit. And they say best fit is this, and they say it is like 0.6 probability that people are going to put jackets. Right? So definitely all the points will not come on this curve, and there will be uncertainty. Sometimes you are putting a jacket, sometimes you are not putting a jacket. Definitely, that's why you got to handle this nonlinearity. Okay, and this is precisely what it is showing. One day you were not putting a jacket, but the other day you were not putting a jacket, and you are putting a jacket, or 2 points may be on the same as well. Okay, so it's got to handle this nonlinearity. So handling nonlinearity comes out to be the same for your basic classifier. If it is greater than 0, it is in one class. It is less than 0, it is in another class. So that thing is not changing. So the good thing about this is that you have the same linear combination of features, weights, and a bias adding up together, and here you put a nonlinearity, and this nonlinearity will make this straight line into a nonlinear curve. Okay, a straight line to nonlinear curve, and this is what you are predicting what you are going to do. And so if you don't put a nonlinearity for different data, it is always going to be a line. Okay, with the weights and the constants, you always going to see a line. But once you put a nonlinearity, it becomes and your basic hypothesis still remains the same. Remember, that is what you were trying to do, that you were saying whether if your equation of a line is greater than 0 or equation of a line is less than equal to 0. So your basic classifier is not changing. So you still have the same linear multiplications, and so all the parameters learning. Now the question is how you make your classifier to learn parameters. And this is, you need to just know about all these terminologies once you are using even any generative AI tool to generate data. So I'll show you that this is what I have used to learn the parameters. Okay, so learning parameters is complex, and we will see that. So this is called the neuron, one neuron, which has all these features and the bytes term, and you adding and generating an output. And then this is the nonlinearity where you add a nonlinearity. And nonlinearities are, so this is one nonlinearity which is called sigmoidal function, and then there are other as well. One is you don't change anything, so it will remain a straight line. The other one is you say I will only convert it into +1 and -1. So this is also kind of a nonlinearity. You are saying it is +1, -1, +1, -1. So it will become end of the day a waveform. This is sigmoidal. This is max 0, means that if it is negative, you change it to 0. And you are not accepting again any negative. And this is also called rectified linear unit. So it is used a lot. Okay. So it is this. If it is negative, you make it equal to 0. If it is positive, you just let whatever the value it has. So negative is converted into 0. And then this is a tangent hyperbolic function there. So people have been using, you will find out this used a lot, you will find this used a lot, sigmoidal used a lot. Okay. So these are the different function. As I was explaining, this is sigmoidal, and this is hyperbolic tangent. Okay, so this is hyperbolic tangent, looks like this, and this is rectifier linear unit, and these are the derivatives. So it says that it should be differentiable because you are going to differentiate the expression. So coming back, you want to create somehow a space, a mathematical function like this. So this is the challenge. Okay, and how are we going to do that? This is now basic thing is that we have this perceptron, and so we are now combining the perceptron. Okay, so features, this is feature are the same, and then there is a constant term which is going to be the same, and this is now, this g function is now going to put a nonlinearity into it. This is again going to put a nonlinearity into it with different weights and different biases. So means one may be something like this, the other may be something like this. And once you combine these two through different weights, it may become something like this. Okay, because now you are combining two nonlinear functions, putting them some weights and shifts, and then adding them together is just going to change the shapes. And if you are adding hundreds of these and thousands of these, okay, so you can just imagine what type of shapes you can actually create. And then if you have so many of them in the depth, hidden layers, yes. So you can just imagine with so many hidden layers, you can almost create any nonlinear function by just letting the computer to learn and fit and compute the loss. What is the loss? If some data is incorrectly classified, it is a loss. You say, no, there is a big loss. Try something else, so adjust the weights. But then it may go wrong as well. So you got to have some hint that whether you are moving in the right direction or not, once you are adjusting weights, okay? And you are saying, okay, perhaps you need to move a little more in this direction, in this direction, in this direction. So that's where,
Is it like having different networks for different number of layers for each?
Yes, different number of layers. So how many layers? Nobody knows. How many hidden layers? Okay. And how many of them in the hidden layers perceptron? Nobody knows. Okay, so you got to do hit and trial. But what people do is, like, they are smart people who have already experimented and developed networks that they work. So best thing is you just copy their network, the weights and everything, which they have, extract all the features, create type of nonlinearities and only trained the last layer, which is, and we will look into this. So mostly nobody tries to train his or her own network because that is very, very costly. And you may or may not even able to create a good neural network. But then there are networks which you can just copy, and they just put it in the public domain, and you can just copy their network and then use part of it, all of it, some of it. May you train some of the hidden layers, may you train all the hidden layers, it's up to you. But at least the structure is there, the architecture is there, that how many layers are there, what is the architecture, those are there. So once you are adding more and more nodes, okay, so first nonlinearity is here, another nonlinearity is here, all sigmoidal for example, another sigmoidal, another sigmoidal. So there are 4 sigmoidal. Now this sigmoidal gets multiplied with some number, this sigmoidal multiplied with some other number, this sigmoidal and this sigmoidal. Again you add and put through another sigmoidal. Okay? So now you can imagine that it's just trying to create a gunjal kind of a thing, and in a hope that that gunjal can have all the classes, thousands of them. Now it's not a binary classifier, like sometimes thousands of or hundreds of classes into it can draw something to basically that can bifurcate all the classes, because it is so highly nonlinear function, and you are just trusting the computational cost that. So it is the game of training these weights, because these are the weights with the sigmoidal, they are changing its shape, number one, and they are moving it left and right. Okay? And in the first layer, you have like these 4, okay, and then in the next layer, again you have more, then again you have more, then again you have more, and depending upon that how deep your network is, and that's what deep neural networks are. That's how it started, like deep neural networks can create almost any kind of nonlinear function to classify your data, and these all operations are linear. So these are the transformation of a vector into, remember, if it is in a 3 dimension, multiplying a matrix will take this vector somewhere else. This is just one part. And once you put it through a nonlinearity, then it is just going to create a nonlinear function. It is no more just a linear transformation. Okay? So this is a single layer neural network where you have only one layer and you have 2 outputs. Okay? And so maybe you have 2 objects, one is a car, the other one is a motorbike, for example. And you want to see whether it is a car or a motorbike, or you want the probability distribution, that how probable it is that it is a motorbike or a car, or maybe nothing. So in that case, you want to see a number here, 0.1, 0.2, 0.6, 0.8. So, so this is a single layer neural network. And a simple example is that these are the weights, 1, 3, minus 2, and those are put, it goes on the left, and then goes through the sigmoidal to ensure that what type of class you want to give it to this. So it put it through this nonlinearity and this nonlinearity, and then you generate an output to this function. And as this is the hidden layer, so it's called the hidden layer. And now here you have another layer. So one hidden layer, the other hidden layer, 2 hidden layers, and then the 2 outputs. So you have added 2 hidden layers because perhaps you are seeing still your loss is more, so you don't like the loss, and you say no, still my classifier is not doing good, so add another layer. Other layer will help you to make your decision boundaries even more nonlinear. So as you are adding more and more layers, you are letting them to be more nonlinear. Okay, so that's what, if you have only one, there is only one sigmoidal. Okay, so I basically here is what I tried to do in ChatGPT, which I would also like you to do as an assignment. I said generate code for a simple neural network that can classify linearly separable data. Okay. So it generated and showed me only 4 points. It said, okay, here is a point which is under this. This is a point in another class, and these 3 points are in another class. So here is the classifier, and says, okay, this is the classifier, which is primarily can neural network has actually trained, or this is the prediction confidence that how away the point is from this decision boundary. Okay, and here it is like with high prediction confidence that it is this point, and we can see that we have done a good job. Then I told it, no, increase the data size. I wanted to still the data is to be linearly classifiable, and I said put more data. So ChatGPT has generated more samples, but clearly it shows that it has restrict them to be linearly separable. Okay, so because I wanted to see first that can neural network though handle this very linear but lot of data in it. So yes, it has actually created this. So this is the classifier designed by the neural network. Okay, then I asked ChatGPT to show me the network. Okay, so it has shown me the network. So there are two features, feature 1 and feature 2. Okay, and there are 1, 2, 3 and 4 nodes in the hidden and one output, whether it is of this class or this class. So it could actually able to do the classification based on 2 input. Then I ask it to show me the weights as well. Okay, write weights as well. So it has actually put in the weights. So these are the weights for these and this, and these are the weights for this and this. These are the weights for this and this, and these are the weights for this and this, and these are the weights for. This is what the weights are trained to give you this classifier. Okay. Then I asked to make it nonlinear. I said I removed the constraint that your data is to be linear. I said just generate any data and show that the neural network through nonlinearities can have decision boundaries that can separate the data very nicely. It has done that. Okay, so some data is here, some data is here, and some data is here, some data is here, and as you can see that it has actually through the same network, it has actually created the boundaries. So so this is, so you can have just generate a neural network and let it figure out. If you give it data, let the algorithm figure out by itself that how many layers it is going to have. The ChatGPT by itself, just give it data and say that design me a good neural network which can do separation of this data.
Can we ask for a mathematical model?
You can mathematical model. I don't know. Maybe that what equation you have at end of the day. Maybe you can ask. Maybe it will generate. Yeah, it can generate because knowing the weights you can generate. Because now you can, as you can see, once you have this, you can write the mathematical expression. Because it is 0.82 x1. So if I write here, it is 0.52 x1 plus 0.14 x2, right? So this, and then negative of this into exponential plus 1, 1. This is this output. It is multiplied by 0.79. So I multiply this with 0.79. Then I write a similar expression for this node and multiply with this. And I write another expression for this node, multiply by this. Then I write expression for this node and multiply by this. This becomes a mathematical expression. And then I can just give it back and see that it is generating the decision boundaries, the equations. So
This was linear, right?
no, it is not linear because 1 plus exponential of minus.
I mean the data was linearly separate.
Yeah, but it is the same classifier which has actually, for this you have to generate, sorry. That was, it is also the same neural network with different weights, So yes, so you got to plot this one. Okay, so you can plot it once you are.
The example of back propagation is done now. It is very complicated, but that explains a lot.
Yeah, so we are just going to do the backpropagation, how the backpropagation works. So SVM can also deal with nonlinearity. It has many Kernel functions, if you remember, the 2010 challenge was using Fisher kernel. So there are radial basis function kernel. And we will spend some time, but what the kernel does is it increases the dimensionality and take these points into a 3 dimension, so that still you can fit a linear classifier to classify this. Okay? So you are not changing your classifier is still linear. But what it is doing is it is just lifting the points into another dimension so that you can fit a classifier. So people have been using these are different kernel functions to primarily handle nonlinearity once you are dealing with SVM. So SVM has some provision, and obviously if you have some provision to have an SVM, so people would rather use SVM rather than, and maybe just use a neural network to extract features and then use this SVM to do this. Now this is what we are talking about, the loss function, that how you train the backpropagation neural network. So this will make us to understand that there are like 2 features. One is how many lectures you have actually attended, and another is that how many assignments you have independently solved. And from the previous record, for example, it shows that people who are here, they get good grade. Either they have solved all the assignments or they have attended all the lectures and they perhaps have bad grade. It's actually data, like I took it from an MIT class. So here is now you want to find out what grade I'm going to get. Okay, so you can just put it through a classifier, and now you are training a classifier. Okay, based on this data, you are training a classifier, and you say I have this test data. It predicts 0.1. So, but you know that actually this guy got a good grade. So actual is 1. So it means you got to adjust the weights. Okay. So to adjust the weights, you got to have a loss function which will tell you that how bad you are doing as a classifier. And how you know? Because you know it is all annotated data. You know the actual answer and you know the answer which is coming from your classifier where you have all the features and the weights and the nonlinear function. So it gives you yi hat for data point I. This gives you actual yi, which is the truth, and this is the predicted value. So all classifiers, they kind of work in this fashion, that you have a loss function, a mathematical expression which can tell you that how bad you are doing. Why? Because iska answer आया 1, iska answer था 0, so you know there is an error in your classification. If still it is in decimal numbers, let's say here it is 0 and you get 0.7, and you know that it should be closer to 0, so there is a loss. So you basically pass all the data points. Here are the actual value, you know the answers. Okay, so this student who attended, like, submitted 4 assignments, attended 5 classes, submitted 2 assignments and 1 lecture, 5, and you know the results from the previous data. Last year, you have this data and you want to make a model to tell students that how important it is, for example, to submit assignments. Otherwise, no matter how good you are not going to get a good grade. So you want to create a model and you start training this model so that you can predict what type of grade a student is going to get before even he sits in the exam. So you say, okay, the first time, because now you randomly put weights here, randomly put weights here, randomly put weights here. कोई number आपने डाल दिया, and you put 4 here, 5 here, and did all the multiplication. This is called forward pass. You do, and your answer is 0.1. And but you know that this student actually passed the course with good grade. So there is an error. You say it has wrongly classified this as fail. Then you put 0.8, and you know it says actually he failed, but it says 0.8. It means your weights are actually problem with your weight. So all this you collect and you sum them up to find out a cumulative loss. And you say, okay, this is the loss, this is the cumulative average loss. And now you go back and adjust these weights. Adjust these weights so that your loss basically reduces. And how you are going to reduce the weights. So this is one function which is called binary cross entropy loss. So most of the time you will see once you are using ChatGPT to generate and train a network, it will use binary cross entropy loss to train your neural network based on you give it data to train itself. Yes. Okay, so this is where it's a binary classifier. Either you have the actual is 1 or a 0. Actual is 1 if you have a plus, let's say COVID positive, COVID negative, okay? Or in our case, good grade or bad grade, 1 and 0, 2 classes. So if good actual is good, 1, so this will be active because 1 minus 1 is going to be 0. So this part of the loss function will not be contributing, only this part will be contributing, where your actual is 1 and it will see the log of the probability that he's going to get a good grade. Why it is using log? Because log if gives you a better, if like it's a large value, so it will penalize you little. If it is small value, it will penalize you more. So log is a good loss function. If let's say the guy failed, okay, so this will be 0, actual is 0, so it will make this expression go to 0, and this y minus 0 will be 1. And here y minus probability, because probability is the probability of he is getting good grade, but you want the probability is getting bad grade because he actually got bad grade. So these are the two functions in binary cross entropy loss. So here is an example. For example, all these, the green colors, they got a good grade, and all these with red colors, they got a bad grade, and this is the data which is available to you, okay? And or wearing a jacket and wearing not a jacket, so you can just in whatever way you want to see this data, and this is the your loss function that you got to find out the loss, that how much is the loss. So you are here, if you are fitting the logistic regression, this is the probability, one perceptron and this. So you see here the probability that he is going to get a good grade because he got a lot of marks, so it is 1. Here as he's been reduced, so here he's so you are calculating the probability of yes, or probability of if it is because it's just one variable, so here it is just one variable, so it is showing you they are positive classes or they are negative classes. So probability of this point to be in the positive class is this much, this much, this much, this much, this much. This is good. The probability of this to be in a positive class is less, and probability of this in the negative class is this much. Probability of this in the negative class is this much. Probability of this in the negative class is this much. So these are the probabilities that you got to compute, and this is your that function. So here is the probabilities of positive, probability of you securing negative, and here is you compute the loss, and this is the loss. Like these are good probabilities that you are going to get a good grade, good, and here is this is also good, this is also good. These two are like adding a little more error into this, but primarily because this is where they are, where there is confusion. Sometimes you may or may not get, but you have a log loss function which takes the probability. If you are at 1 already, like you have correctly classified, the loss is 0. If you have wrongly classified, there will be a big penalty. So you got to have like take mean of this, and this mean divided by 1 over n give you the loss. Let me just show you with this example. This will just help us to understand. Okay, so you have only 2 classes, a data which has only 2 classes. One is, let's say you get a good grade, 0 is you get a bad grade. 1 is you get a good grade, 0 is you get a bad. So this is an annotated data. After passing through the classifier, okay, your neural network, it gives you a number which says this is a probability that you get a good grade. So only one probability that you get a good grade. Okay, it says 0.94, 0.90, 0.78, 0.56, 0.51, 0.47, 0.32, 0.10. These are the probabilities which your network has calculated. Okay, and now you want to adjust the weights, finding out what is my loss. And how do you find the loss? You say, okay, this is if it is 1, good grade, you are going to keep the probability as is, because the probability of getting a good grade, and this is the probability of getting a good grade. But if actually it is 0, and the probability that you have calculated, your network has calculated, is probability of getting a good grade. So you take 1 minus this to find out probability of getting a bad grade. And because you want to see the probability of getting a bad grade in the loss function, not probability of him who has gotten bad grade, you don't put this probability, rather you put this probability because he has gotten a bad grade. So network is giving, so this is the only understanding that you need to make. The network is always give you probability of getting a good grade. Okay, network only tells you probability of getting a good grade, but the loss is if he has actually gotten a bad grade, you got to find out the probability that he has gotten a bad grade. If this value is low, okay, there is more penalty, means there is more loss. But this value is high, once you take a log, you find very small numbers. So the loss is very little. So actual was 1, and the probability of him getting is 0.94, very little loss. Actual is 1, probability of him getting a good grade is 0.9, very little loss. 1, 0.78, the probability of getting a good grade is 0.78, where he got a good grade, loss is a little more. And now 0, and probability of getting his good grade is itna, so probability of getting a bad grade, because actually he got a bad grade, is 0.44, which is not that good. Okay, so you see that there is a more loss, which is 0.35. 0 here is 0.5 of good grade, so 1 minus 0. This, so again a great loss. 1, 0.47, as you can see that he has done a poor job, the classifier has done a poor job, so it says 0.47 and it says minus 0.3. So similarly 1, poor job, more penalty in the loss function. 0, very good job, 0.10, probability of getting a good grade because he got a bad grade. So probability of getting a bad grade is 0.9, so very little loss, so a very little loss. Okay, so you add all these together to get a loss value, and this is what is plotted. So once you are training, it is going to show you that whether you are improving on the loss or you are going bad. So the other function is the mean square error. Instead of log, computing the log, you simply have the actual value and the predicted value, and you square it, and then this is also give you a loss function. Okay, but I have seen mostly this is used, which is the cross entropy loss. Now the loss optimization is that somehow you need to, this is the only thing you have in your hand, the weights. And if you write an equation is x1 w1 plus x2 w2 plus w0. For example, this is your equation. x1 for a sample point is fixed, x2 for a sample point is fixed. Okay, and w1, w2 is currently you have something and you want to update this so that you reduce the loss. Okay, because w1, w2 or w0, all these are the parameters which you want to reduce the loss. And so you have this loss function which we saw is the log of something and stuff, or the square, mean square error. And so you want to see that how this surface looks like, and you got to update these weights, and you find out that for example, because of all the nonlinearity you have built into the system, the surface becomes very, very complex. Because the weight is not linear, it is not a linear equation, or even if you square it, it is not simply a parabola that you just take a derivative and get 0. So the error surface becomes very, very complex. Okay, And actually somebody has, let me show you. This is the array surface of ResNet. So it is very difficult to reach to this point, which will minimize the loss. So they have done this simulation to show that you got to search in the space of all the weights, and somehow you got to find out the minimum, because there is just no way that you can just directly mathematically figure out the formula like we do if we have a quadratic equation. We just take a derivative, put it equal to 0, it'll give us the point, which are the minimum or the maximum, you find out minimum or the maximum. That makes it very, very complex problem to actually solve, that loss minimization problem. First is, you have to just randomly select weights, okay? So there is a network, you say all the weights, and you compute the loss, and you find out loss is too much, and you are here, okay? This is too much loss. And the figure will tell you, say, oh, this is a big loss, that every loss is too much. And now you want your weights to be adjusted so that you move in the loss to somewhere which gives you the less loss. And one method is that you take its partial derivative. It's a little mathematical, but you move against the gradient. So once you calculate a tangent of a surface and you move against the tangent, so you are moving down that surface. In the loss surface, you are moving down. So the technique here is that you compute the tangent or the gradient at that point and move away from the gradient. So move away from the gradient in a little step. So move away in a little step, move away in a little step. And for that, you got to take the derivative of this loss function with respect to all the weights, and then every weight has to be adjusted through this iterative method. And by doing this, you can slowly can get to and there is no surety that you get to the global minimum. There is no surety, okay? You may hit a local minimum, okay? So this is the algorithm. You initialize randomly weights, and then you compute the gradient, and then update a weight, and this is the step size, a little step in going down. Learning rate. So this is called the learning rate. And then you go back and keep checking, okay? So let me not get into the maths of this, but here is the surface that you are in, and you are trying to find out where you have only very little vision of the point where you stand, okay? So sometimes they try to make the surface a little better by removing some of the nodes, some of the nonlinearity, so that they say, let's try to skip connections, because every connection is adding nonlinearity. So they say, loss function is very, very difficult to optimize, okay? So, but you are moving against the gradient. This we understand, because this is the minimum point. If you move against the gradient a little step, there is a simulation which shows, okay? So here you can see that you are moving against the gradient. But if you take a big step, so you may hit another point. Instead of reducing the loss, you may start increasing the loss, okay? So sometimes you may have very small step, it will take you forever. Sometimes you have too big step and you keep oscillating. Less loss, more loss, less loss, more loss, less loss, more loss. Finding this is really challenging, that where you are actually reducing the loss and you have a step, the learning rate, which is not going astray, and so you are in the surface, and sometimes, so you got to have this loss, you got to remove this. Very high learning rate is bad, low learning rate will take forever, high learning rate will just give you non-optimal, and good learning rate will give you the best learning rate. So this is a simulation where you can see it start reducing the size once the gradient is becoming smaller. So gradient is becoming smaller, and it is not doing that, so it is just oscillating. This has a fixed learning rate, this has a dynamic learning, adaptive learning rate. So once you are even asking ChatGPT to generate a network and to make it learn, it is going to use an adaptive algorithm where it will see the value of the gradient and reduce the step size, okay? And then it will try it many times, because once you are trying, the starting point also matters, that from where you start. You may just end up in a local minimum. So You try from different starting points and try just everything, so that the good thing is that you know the loss. So the good thing is that you know the loss function, and I'll go to, so these are the algorithms. One is stochastic gradient descent, it is adaptive movement estimation, adaptive delta. So the delta step, it is making it adaptive. So there are adaptive gradient, and so RMS prop. So there are many algorithms, and primarily focus is to make them adaptive. Okay? So the challenge is you are never sure. You may have a local minimum, you may overfit, you may. So all these are the challenges. Computational cost is among us. And that's why people were not using neural networks, because it requires so much computational power to train a neural network. Once it is trained, it is very fast. Okay? But once the training would require a lot of efforts, and you are fitting non-linearity if you overfit. Okay, though there may be just a line which could best represent the training set, but you try to overfit, then it will just overfit. It'll create that non-linearity, which may not be actually good. Once you put your training data, you find out that this is not a good classifier, because it has actually tried covering every point in the data where it should have just captured the trend. Okay? So this is called overfitting. Now, how do you deal with overfitting? Usually it says reduce some of the nodes, reduce some of the nonlinearity. This is how you can deal with it. The second is early stopping. Though you are improving, and you say, I will stop here. Because now, though you are doing better training, this is the training set, you are minimizing the loss. Okay? But once you put the training, you find out that you are doing really very bad because you're doing overfitting. That tells you that you have overfitted. So how do you find out whether it's overfit or not? The training loss is getting better, but the testing loss is increasing. It means there is an overfit. So there is an overfit, that you have overfit the curve, and it is in such a way that every point, it is almost passing through every point of your training data. But definitely the test data is going to be somewhere else, and it'll start giving you more errors. So this is called the overfitting. Okay. So this is pretty much the first part, which I just kind of recapped. So these are the deep neural networks. And what do you do if there is an image, or even there is a 1D signal? So whatever we are studying is valid for 1D signal as well. Okay. If it is a colored image, then every pixel is an input. That makes it very, 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 very complex. For example, if it is 258 by 258 by 3 size image, you can just imagine how many inputs. And then in between, you are going to have multiple of these nodes and multiple of these weights, and then you are doing the classification. So the challenge in deep neural networks are that they are too expansive computationally, and the memory they would require, and the number of weights you got to train. And we have seen that how you train. Every weight you got to train through this iteration. And you have to run it millions of times. That you have to run it so many times to get those weights adjusted. So it becomes a challenging problem. So I asked neural network, ChatGPT, to generate a loss function while training a neural network. Okay. So this is where this is interesting. So it has like, so this is the sigmoidal function it is using, and it has these are the inputs, 2 inputs. Hidden layer has 4, and output is 1. Okay. And then it is the learning. It has 1000 here. This is the learning rate. 0.1 learning is 1000 epochs. So you can change this epoch to 10, 20, 100, 200. So this is the number of times what I showed you. That number of time it is going to adjust the weight. So it may overfit if you run it so many times. Okay. So I took this, and here you can see that it is going to, this is predicted output. So this is the error it is calculating. Okay, error is actual minus predicted. Okay, and then here it is updating weights and biases. So weight plus equal to. So weights of the hidden outputs and the bias, it is going to do that. With the, it has to do with learning rate. So this is the learning rate. Okay, learning rate is 0.1. So every time it is making a little adjustment to the learning weights. So does the learning weights, these are the weights of the input hidden layer, bias hidden layer. Okay, and here I wanted to also plot. So it will do the plotting as well. And so this is the neural network we earlier saw. These are for 10,000 epochs. And I could see that it has done really good because it's a simple neural network. You don't have to run it 10,000 times. So I said run it 10 times. So 10 times still I had some training loss over epoch. So still I have some error. So I said do it 20 times. 20 times almost it hit 0. So it started with the random weights. It started with 0.40. Next time 0.35. It went up. Then it came down. It here. So just keep changing. And if you look at the so labels, initializing weights, learning rate, loss calculation, forward propagation, this is back propagation where it goes first, find out the predicted output, then it comes back and adjust the weights again, hidden layer, update weights in the hidden layer. Yes. So it's interesting that you could actually find out that how it is generating all of this for you to just use it. So this is again okay. So let me just take 5 minutes and then we will. So this is a fully connected neural network. Okay, and deep neural network means that you have many of these layers, and this means here you have output, but the classifier is going to be highly nonlinear. Okay, highly nonlinear, which is just classifying each of this into whether it is in this class or not in this class, basically. And if you have an image, which we started with, like this is the data set where, so these are the weights. Weights are like 10 images, there are 10 classes. So you take an image, every pixel is basically an input. So you multiply all these with weights and then you find out that which one is the largest one. And so, and the other way is that you extract features. So manual feature extraction is very cumbersome. We have seen this, okay, very cumbersome, and it's like take you 3 years to complete this, almost 3 years to do your thesis, because you are just all the time just figuring out. And then obviously you got to do the annotation as well, that how many times actually you have figured out the lesion, which is whether it is the right lesion or not, because so you got to have an expert who would, every pixel he would annotate that yes, this is lesion, this is lesion, this is lesion, and then you see the accuracy. So the accuracy of candidate lesion finding out itself is very complex. Okay? So so many problems. You've got to have domain knowledge. You need to define features. You need to do the feature extraction. Then there's deformation, occlusion, background clutter, this and that. So feature extraction really becomes, even there are PhD theses who would only segment an image, segment an object, okay? Because segment, it becomes so difficult to do. Segmentation becomes a very difficult problem, where from the clutter you have to extract the object, and then you are going to do the classification. So this is very difficult. So you want something which you, without you worrying, would extract features for you. Low-level features, mid-level features like the eyes, ears, nose, edges, dark spots, and high-level features, the complete face. Okay, it come as a feature. So you want a technique which can automatically do all of this for you. So this is where we use convolutional neural networks. So convolutional neural networks, I'll just come here. अच्छा, convolutional neural networks जो हैं, I think we can let's just take a break 15 minutes and okay, now we